moving up in the air and then falling down. So these equations given by equations of motion, they are actually basically what governs the motion of these bodies. But then most of the things we see around us that are rotational in nature. When we talk about physics, we talk about space, we talk about planets, we talk about galaxy, they're all rotating. When we talk about atoms, we talk about electrons, we talk about how we have got diatomic structures, we have got molecules, how hydrogen exists as two atoms forming a bond, it may be rotating. So rotational mechanics is a very important topic in physics. And of course, from exam point of view, from competitive exam point of view, it's a very important topic as well. So let's understand the basics of rotational mechanics. I will take you on a journey around rotational mechanics, the various concepts and the formulas involved in solving problems as well. So when we talk about linear motion, we usually talk about how an object is moving from one point to another. Yeah. So how an object that moves from one point to another, and when that object moves, it undergoes a displacement. So an object can move from O over here and it can go up to this first blue point that is given over here. And in such a case, the displacement of the object is usually denoted by S or X. If it's along the X axis, we call it X. Sometimes it may be along other axes as well, so we'll call it S. And then the time taken by the object, because as the object is moving forward, time is constantly changing. And as the object starts from O, we consider the time to start. For example, we take a stop clock and start the stop clock. And then that object takes a few seconds or milliseconds or microseconds or maybe a few hours to reach from point O to this first point over here. So this time taken T and this displacement S gives me something known as velocity. So when I talk about velocity, what is velocity? It is the rate of change of this displacement. So in linear motion, we delta S by delta T or S by T, get V. But when we talk about velocity, we want to know things now. I don't want to know after half an hour what is the velocity. I want to know now. In which case we take small movements, not from O to this point. We take from this one point to the second blue point, and we take the small changes delta S and delta T and find the rate of change of this delta S will give you the velocity, which is given by this vector over here in blue. And that velocity can also change. Okay, the rate of change of velocity can also happen. Velocity may not be constant, in which case we call it an acceleration. And of course, because velocity is dx by dt, dv by dt can be written as double differentiation of x or d square x by dt squared, which we call it as a. We put a arrow marks on top of this x, v and a because they are all vectors. They all have one direction, not just a magnitude. Then we have something known as momentum. Momentum is basically how an object of mass m moving with the velocity v will impart its motion into another object. So when it collides with one object, it will impart this motion that it is having into another object. So that is given by momentum. If the momentum is large, for example, if the mass is large, the object is said to have high momentum. Or a small object of small mass is moving very fast, very high velocity, then it is said to have high momentum. So this formula here is given by P is equal to mv. Then, when the momentum changes with respect to time, the rate of change of momentum is said to be force. So basically, Newton's law, he says that rate of change of momentum gives us force. Okay. Oh, I made a mistake over here. It's dp by dt. Okay, so it's dp by dt, dmv by dt, which gives me m dv by dt. dv by dt is nothing but a. Please ignore the 2's over there. It's by mistake. So dv by dt is a. So m into dv by dt is m into a, which is equal to force. And we all know this equation, the Newton's equation of force, that is F is equal to ma. So all of these things are very simple, very easy. Okay, but these are all linear motion. And once we have this linear motion defined, we know acceleration is equal to dv by dt. We can change a few variables. Okay, change in v, dv is given by final velocity minus initial velocity. And again, I don't want this vf, vi and so many v's in the equation. So final velocity, I'll call it v. Initial velocity, I'll call it u. So v minus u, which is the change in velocity with respect to time, will give me this equation. V minus u is equal to at. This is the first equation of motion, or we can write it as v is equal to u plus at. All of you are familiar with this equation. Similarly, displacement can be calculated if you know the acceleration and velocity using this equation. S is equal to ut plus half at square. And we have the third equation, v square minus u square is equal to 2as, which is also an equation of motion. So depending upon what you know and what you want to find out, you can use either of the three equations to find out the velocity or acceleration or displacement or the time taken to reach certain displacement. Now, when we talk about rotational motion, what happens to these equations? This is something very important. When we talk about rotational motion, things are not moving straight anymore. Things are moving in a curved path. And when I say rotation, it's usually along an axis with respect to an axis. So you can see the stop over here. The stop is rotating. Okay, the stop is rotating with respect to this vertical axis over here that is given. And if I want to find this curve, what is this curve? Then it is basically a circle of radius. This lines given here, these dotted lines given here. So circular motion is rotational motion, but not all rotational motion are circular. There may be a part of a circle that may be a rotational motion, and so on and so forth. And when we talk about rotational motion, we'll come across so many different terms which we are here to find out. So when we have linear, any property that is linear, in rotational motion, there is an equivalent angular property. It's not equal, it is equivalent angular property. So for example, we have displacement. In rotational motion, we've got angular displacement. In linear motion, we've got velocity. In angular velocity is the rotational velocity. In linear motion, we've got acceleration. In rotational motion, we've got angular acceleration. In linear motion, we've got momentum, we've got angular momentum in rotational. And in linear motion, we've got force. And in rotational motion, we call it angular force, or we call it torque. So before we talk about rotational motion in detail, because I'm talking about rotation, I'm talking about circles. And when we talk about circles, pi is a very important quantity. So pi is usually defined. How do you define pi? You take a circle and its width, which is the diameter, and you basically put these circles next to each other of the same diameter. And then along this line or along this width that you've got, you trace how big is the circumference. And you'll find that for all circles, this circumference over the diameter, this ratio of circumference to the diameter will always be this value that is marked over here, that is 3.14. So the ratio of C by D is equal to pi, we call it. Okay. Or from this we get the formula C is equal to pi D, cross multiplication, and D is nothing but 2 times the radius. So if you know radius of any circle, you can calculate its circumference using the value of pi. The value of pi is 3.14. Okay. It's not exactly 3.14, it's a never ending irrational number, but here onwards we'll consider it as 3.14. Now, because we are talking rotational motion, I said that in linear motion we've got displacement. In angular motion, we've got angular displacement. So consider this motion, let's say along this arc that you see over here. Okay, I hope the mouse is visible. Along this arc, you can see that this is a rotational motion. Something is moving along this arc. So as something moves along this arc, it subtends an angle theta. Okay, it subtends an angle theta. So the object starts from this junction over here at this point. And from here, the object starts moving, and goes along this path. Let's say the object travels from this point to this point over here, okay, where the red triangle meets the arc. The object moves from this junction to this point over here in time t. Then this distance traveled by the object along this curve unto this point in time t is known as the angular displacement. Okay. So let's take this triangle over here, because as the object goes from here to here, it subtends an angle, which is theta, which is nothing but the angular displacement. So we'll consider this red triangle over here. And once we know theta, we can calculate sine theta and cos theta. Okay, for a radius, unit radius, we can consider all these things. So if I take sine theta in this red triangle, we'll get this as the ratio of this distance, this arc, which is equal to this movement over here, and r, the hypotenuse of the triangle. Because sine theta is opposite by hypotenuse, we get s by r. Okay, this is only valid for very small angles. Otherwise, this arc becomes not equal to that vertical height. But let's assume that it's a very small angle. Then sine theta is equal to S by R. And when theta is very, very, very small, I can write sine theta is equal to theta, right? And this theta is my angular displacement. So if sine theta is equal to theta, I can write theta is equal to S by R, or I'll cross multiply and write S is equal to R theta. And this is the formula for angular displacement. Okay, when an object moves a distance of r or a displacement of sorry, an object moves a displacement of s along a curved path such that the radius of the curved path is r, then its angular displacement is given by theta. So theta is equal to s by r, or we all know the very famous formula s is equal to r theta. This is known to us. Now, when we talk about rotational motion, we'll come across this radian concept. So what is a radian, if you ask me? It is the angle subtended by an arc whose length is equal to that of the radius. So an object is moving along a curved path or a circular path, and when the object has moved enough distance, which is equal to the radius, we say that is 1 radian. So we have got the formula S is equal to r theta. And when we say the length of the arc should be equal to the radius, we substitute S is equal to r. And then you just substitute that in the formula. You get r is equal to r theta, or theta is equal to 1. So we define 1 radian as the angle such that the displacement S, or the arc length subtended by this angle theta, or 1 radian, is equal to the radius. So from this, we can also equate that the displacement of this object is not equal to the radius, but equal to the entire circumference of the circle. So when S is equal to C, we put S is equal to r theta. So we put S is equal to C, we get C is equal to r theta. And then, of course, theta for the entire circumference, the angle subtended is 2 pi. So we put C is equal to 2 pi r, right? And from this, we get that theta is equal to 2 pi. And this is why we say pi radians, or 2 pi radians, is equal to 360 degree. Okay, because it's a complete circumference, complete circle. The entire angle subtended is the full circle. So 360 degrees is equal to 2 pi, or simply pi is equal to 180 degrees. Here this pi is given in terms of radians, and that is why we call pi radians is equal to 180 degrees. In all of rotational mechanics, we put pi in terms of radian, or 2 pi radians is equal to 360 degrees. Okay, so this is the formulation that we'll be using. So once we've covered angular displacement, let's talk about angular velocity. In linear velocity, we have got velocity is equal to displacement by time, or rate of change of displacement. So similarly, in angular velocity is nothing but rate of change of angular displacement. So if I want to find the angular displacement's rate of change, I will take, let's say, rotational velocity v rotational is equal to d theta by dt, where theta here is the angular displacement. So d theta by dt, I don't want to write this v rotational and also. So let me just put an omega symbol, another Greek symbol, omega. So angular velocity is known as omega, which is the rate of change of angular displacement, or omega is equal to d theta by dt. But we know that theta is equal to s by r, okay, because s is equal to r theta. So we substitute that. Now when you're differentiating this, okay, we've got d by dt of s by r, we need to see what changes with respect to time. Between s and r is the radius of the circular path, and that will never change. Whenever something is going in a circular path, the radius is assumed to never change except for special cases. So r cannot be differentiated with respect to time. It's a constant. That is why we take 1 by r into the changing variable, which is s. So we've got ds by dt into 1 by r. So this is your omega. Or let me just cross multiply, take r on the other side. We've got r omega is equal to ds by dt. S here is the displacement, the linear displacement, or the arc subtended by the object. So S is the distance divided by time, which is nothing but velocity. So distance by time gives you velocity. Therefore, V is equal to R omega. This is something we'll be using hereafter. So This is another formula that relates rotational motion to linear motion. We had got S is equal to R theta, where we said angular distance is equal to radius times angular displacement. Similarly, here we've got V is equal to R omega, which says linear velocity is equal to radius times angular velocity. So it relates V and omega. This is something we may be asked sometimes. Okay. Now let's understand the directions, because these are all vectors and they are rotating. Now when I say rotating, the vectors usually keep changing the direction. The angles keep changing the direction. So I need to understand the direction of this angular velocity. So let's consider an object moving along this arrow, black arrow over here. Okay. Let's consider an object that is moving along this black arrow of radius, let's say r. Okay. So it's moving with a radius r. And at every single point along this curve, this object has a tangential velocity v. Okay, so we've got the radius r, which is same along this entire curve path, and the velocity keeps changing direction at every single point. We call it tangential velocity or linear velocity. So you put v is equal to r into omega. Okay, it's actually v is equal to omega cross r. Okay, that's the angular, because these are both vectors. When you multiply two vectors, you need to be very careful. And this is the actual vector formula. So you see there are arrow marks on top of V, R, and omega. So V is equal to omega cross R. Now that means whenever there is a cross product, A cross B is equal to C, then we know that A, B, and C are all mutually perpendicular. So let me show you. We've got R vector and V vector like this. I'll connect both of their origins at one point. Okay, I can do that. So I move the vectors from the top and bring it over here. So we've got V vector and R vector. And because omega cross R is equal to V, V should be perpendicular to both omega as well as R. Okay, so V should be perpendicular to both omega as well as R. And this is only possible when we've got omega in the vertical direction along the axis of rotation of the top. So this is the direction of angular velocity. Although the linear velocity keeps changing direction along the rotational motion, at every single tangential point, it is going to point one or the other direction. You can see, I'm not sure if you can see the mouse, but at this point, the velocity is along this green arrow. At this point over here, the velocity is going to be tangential. At this point, the velocity is going to be tangential. So the linear velocity keeps changing direction, but because it is a cross product, omega cross r is equal to v. Because it's a cross product, this omega should always be perpendicular to v and always be perpendicular to r. So you can see as velocity keeps changing direction over here, omega will remain in the constant direction, that is upward direction in this particular rotational case. Now, when we have multiple rotations, what do we do? If it's single rotation, a car going along a circular path, no problem. A stone going along a circular path, no problem. But when it is undergoing multiple rotations, we can basically say it is going so many times in 1 second. So many times it's rotating in 1 second. So the rotations are numerous, and that is why we will come up with this term called frequency. Frequency is basically number of cycles per second in all of physics. So when you're learning waves or anything else, we say frequency is number of cycles per second. In case of rotational motion, one complete cycle is nothing but one complete rotation. Therefore, any object that is going in a circular path, the number of rotations per second is given as the frequency of this rotation. And this frequency is directly proportional to angular velocity. So this proportionality constant is nothing but 1 by 2 pi. That is why we can write f is equal to omega by 2 pi, or omega is equal to 2 pi into frequency. So if an object is rotating 1 times in 1 second, or it's rotating 10 times in 1 second, then the frequency is given by that number multiplied by 2 pi, you will get omega, which is the angular velocity, or we also call this angular frequency. Okay. Now we know that S is equal to r theta, and we know that V is equal to omega r. So I can write omega is equal to V by r. Okay. And from that, I'll get all of these formulas that are shown on the screen. And along with frequency, I will also consider a property called period of rotation. A period of rotation is the time taken for the object to complete one rotation. Frequency is in 1 second how many rotations. Time period is one rotation takes how many seconds. So if an object take 1 seconds to complete f rotations, that is the frequency, and the object takes t seconds to complete one rotation, then you cross multiply, you'll get t into f is equal to 1 or t is equal to 1 by f. So if you know the frequency of rotation of an object, you can calculate its time period as t is equal to 1 by f. Now speaking of angular velocity, angular displacement, of course there's also acceleration. If you know displacement, you know rate of change of displacement is velocity. If you know velocity, then rate of change of velocity is acceleration. Similarly, rate of change of angular velocity gives you angular acceleration. So angular rotational acceleration is equal to rate of change d by dt of omega. I don't want to write this a rotation and subscript and so on, so I'll call it alpha. So alpha is my angular rotation, which is equal to d omega by dt. Okay, so we'll call this alpha as the angular rotation. Now again, omega is v by r, and when I do d by dt of this quantity over here, I need to see which is a changing variable and which is a constant variable. So you see here r is a constant term. Okay, the radius of the rotation will not change, and velocity can keep changing. Okay, velocity can keep changing, and that is why here when you differentiate with respect to time, you will only consider the velocity because that is the object changing with time. And r is considered as a constant, so we've got 1 by r into dv by dt. Now what is dv by dt? V is the linear displacement, v is the linear velocity. So dv by dt is the rate of change of linear velocity, which is nothing but linear acceleration. So I've got 1 by r into, this is the same thing. I've just cross multiplied r in with alpha. So r alpha is equal to dv by dt. So dv by dt is a, and therefore a is equal to r into alpha. Again, I'm relating angular acceleration with linear acceleration. Linear acceleration is equal to radius times linear rotational acceleration or angular acceleration. So this is another formula that we'll be using for problems later on. Okay, so these are very basic formulas. S is equal to r theta, V is equal to r omega, A is equal to r alpha. So every single time linear term is equal to r into rotational term. What is the direction? Again, if we consider the vectors, it is alpha into r, not simply r into alpha. Alpha cross r is the cross product vector multiplication. So we've got the top, we've got the radius, we've got the velocity, or as the velocity changes, it's also the acceleration direction. So we had the earlier case where velocity initial, consider one case of velocity, was given this direction. So omega was this direction. Now as the velocity changes from vi to vf, acceleration is vf minus vi, and at the same time, this is the change or this is the direction of acceleration. And similarly, angular frequency or angular velocity, when I consider, that is also going to change as there is an acceleration or there's a change in velocity, and that change is going to be along the same direction. Now, because omega f and omega I are along the same direction, your acceleration angular, that is alpha, will be along the same direction. Okay, so A and R, they are both perpendicular to alpha. This is something very important. Now, so far, we have covered acceleration and velocity and displacement in rotational terms. We know the equations of motion, V is equal to U plus AT. And we know what is V. V is the final velocity, linear. U is the initial linear velocity. A is the linear acceleration. T is time. Considering the same formula, I can also substitute this or replace these terms with the angular terms such that final velocity, I can write it as omega f. Initial velocity, I can write it as omega I, all are rotational, and acceleration is alpha. So this formula V is equal to U plus AT becomes omega final is equal to omega initial plus alpha into T. It's the same thing in rotational. Similarly, S is equal to UT plus half AT square. That becomes theta, which is the angular displacement because S is the linear displacement. Initial velocity is U, so here it becomes omega I. T is T, that will not change. And we've got half A, which is alpha in rotational terms, and T is the same. So theta is equal to omega I into T plus half alpha T squared. And similarly, for the last equation, final velocity square is equal to initial velocity square plus 2 times acceleration into angular displacement. So that writes like this. Omega F squared is equal to omega I squared plus 2 into acceleration, that is alpha, into displacement, that is theta. Fine. So these are the motion. Now, when I'm talking about rotational motion, I'm talking about an object moving along a curved path, and this object usually has mass, right? This object usually has mass. Now, mass in physics is what decides inertia. I hope all of you know what inertia is. Inertia is the tendency of an object to remain in the state of motion. So similarly, when something is rotating, the tendency of an object to remain in a circular rotating motion is inertia, rotational inertia. And that is said to be moment of inertia, which is given by I. And m is the mass of the object, r is the radius of the object, then we can say I is equal to mr square. But when I'm talking about rotational motion, let's say for the solar system, it's not one entire mass of the solar system. The solar system does not have one big radius. We've got different planets moving around the sun. Each of these planets have different masses. Each of these planets are at a different distance. Or for example, when I take a stone and rotate it along a curved path using a thread, then that stone has multiple pieces, because when you drop a stone, it can break into smaller pieces. Each of these pieces has mass m, and each of these pieces is located from the rotational axis at a distance r. So when we've got multiple masses and multiple radii, we can write moment of inertia as an integration, the sum of all of these continuous terms, r squared into m, or here in case of integration, it is dm. Right? This is known as moment of inertia. So just like mass is there for linear momentum, linear motion, we've got moment of inertia for rotational motion. Not mass for rotational motion, moment of inertia for rotational motion. So for different objects, its radius keeps changing, its particle distribution keeps changing. That is why every different object has its own formula for moment of inertia. For example, when you take the cylinder with a large radius over here on top, along an axis which is given by this dotted line and this radius r, it has a moment of inertia of 1 by 2 mr square. At the same time, a similar cylinder of length L and a very small radius, we can say the radius is negligible, with the axis passing through this center over here, has a moment of inertia of 1 by 12 ml squared. L is the length over here. Okay. Similarly, for the first cylinder, the axis was through the faces. Now, let's consider another cylinder over here, given at the bottom, the first one at the bottom. The axis is passing through the cylinder like this, in which case its moment of inertia changes to 1 by 4 mr squared plus 1 by 12 ml squared. Okay. You don't need to know how this moment of inertia formulas come in, because they come in higher studies, but then every object has its own moment of inertia formula depending upon the same object's axis of rotation. If you change the axis of rotation of an object, the moment of inertia will change. Then we'll talk about momentum. Linear momentum is equal to P is equal to m into v, where m is the mass, it is what decides the inertia, and v is the velocity. Similarly, angular momentum, let's call it L, is given by I into omega. I here is the moment of inertia. I'm not substituting mass, because I told you, just like mass is some amount of substance for inertia to act upon, I is some amount of substance distribution in a rotating object for the rotational inertia to take power. So L is equal to I omega. This is the formula. So I is equal to mr squared. I showed you that in the previous slide. So L is equal to mr square into omega is equal to V by R. So I've substituted all the formulas I knew for I and omega. And here in the mr squared, the R will cancel with this denominator R. So I've got L is equal to mvr. Now here, if you consider the vector terms, V and R are both vectors. L is also a vector. So you can't simply multiply two vectors. You need to have either a dot product or a cross product. And because it's a rotational motion, we will get a cross product of the two vectors, that is R and V. Mass is a scalar, you leave it out, you're going to just multiply it. But R and V are both vectors, that's why we write the cross product like this. Now again, let's try to find the directions. We have a rotating or a spinning top with radius R, a tangential velocity V. Okay, yeah, I'm just tracing it with you. So we've got tangential velocity V, radius R. If I connect these two vectors at the base, then the cross product of R and V will give me a new vector L, which is going to be perpendicular to both V and R. This is something very important. So V and R, when you find the cross product, you'll get L. And of course, when you learn physics, you'll come across thumb rule. Okay, you will have heard of thumb rule in, if you're in second PU, you'll have heard of the thumb rule when we talk about electricity and magnetism. But whenever we have something rotation like this, the thumb rule is what guides us towards the direction of angular momentum. Such that if the four fingers, when you form a thumb, the four fingers form the direction of the rotation, then the thumb will tell you the direction of angular velocity as well as angular momentum. So this is something we'll be using many times in physics. Now, conservation of linear momentum, ignore the formula at the bottom. Conservation of linear momentum is equal to m1v1 plus m2v2 is equal to m1u1 plus m2u2. Or we say the initial velocity and the product of mass or initial momentum of the object 1 plus the initial momentum of the object 2, the sum is equal to the sum of the final momentums. So this is what the linear momentum conservation says. Similarly, if I want to talk about angular momentum, is it conserved? Yes. But how do we get this? When you consider in terms of linear motion, you put F is equal to 0. Then from Newton's law, dp by dt is equal to 0 because dp by dt is equal to F. Or dp by dt is equal to 0 means m is mv, which is p. P is equal to mv. That is constant. So if d by dt of p is 0, we say p is equal to constant or mv is equal to constant. Similarly, in angular momentum, I will consider when the angular force, okay, we'll call it tau for now, is 0, then the angular momentum, the rate of change of angular momentum should be 0. Okay? And if I say angular momentum, its rate of change is 0, which means it does not change, then I say angular momentum is a constant. So in the absence of an external rotating force, angular momentum is constant. Angular momentum is given by L is equal to mvr. So I say mvr is equal to constant. This mvr can be initial or final. So initial mvr is equal to final mvr, or simply I write mv1r1 is equal to mv2r2. Now please understand, this is a balancing equation. If the radius increases on one side, then for the constant to be maintained, the velocity has to decrease. If the velocity increases, then the radius has to decrease, such that mvr will always remain a constant. Okay, we'll give you a few examples. Okay, let me just not show you formulas all the time, so I'll show you some videos. Angular momentum is basically a vector, so it has a direction, it has a velocity, rotational velocity, and a radius. So a spinning object will have its momentum conserved, and because this momentum is a vector, the direction which is perpendicular to the spinning motion will be conserved. So let me play this video. This is gyroscope that is kept in space. So when you just push the gyroscope in space, it will simply flip like this. You can see it's just randomly moved. But now what he does is in space, he will give it a fast rotation, and now the disk is spinning. And now no matter how many pushes he gives it, the object will always make sure it is upright, because the axis of rotation or the direction of angular momentum will remain a constant. Let me show that again to you. So when he pushes this object here and there, you see it is going to just move around, just topple around. But once he gives it a spin, that axis of rotation, that direction of angular momentum will always point. Because when he rotated it, that was the direction. See, when he rotated it, when he held it, that was the direction. And when he released it, after that, nobody's touching it. And even if you touch it, that direction will remain a constant. Okay, so in the absence of external torque, unless he's causing some force to rotate, not push, rotate, a rotational force is not there, therefore it is constant. You can find this YouTube link here, and you can find this video on YouTube and watch it for yourself. Similarly, when you consider a bike race, you see they bend the bike so much. They bend the bike so close to the ground, yet they do not fall. Why? Because the tires are spinning so fast, there is a radius to these tires and the velocity is very, very, very high. There is an angular momentum vector along this yellow arrow, which you can see. And as the bike, he leans the bike, this arrow's direction will change. But because angular momentum cannot change direction, the bike will come back to that position. So no matter how close he goes to the ground, he will not fall because the bike is going to go back to that same position. Okay, so this is how it is used in MotoGP. So just to give you an idea, this is the angular momentum. Another beautiful example here of conservation of momentum. You can find the video on YouTube. You can see MVR is equal to constant. So initially you see it's a very big ball of large radius, okay, and its velocity is small. Initially at this point, you can see now velocity is small, radius is large. And as he pulls this thread, the velocity increases and the radius becomes small, such that the product of velocity and radius with this mass is going to be a constant. Okay? So as the velocity increases, radius decreases. What you can change here is the radius. So as the radius decreases, velocity increases. Another example is using an ice skater. An ice skater, when they rotate like this, they bring their arms close to their body. You can see now the arms are spread out. And when they bring close the arms, they spin faster because the velocity increases. Okay. Now, talking about angular force, I told you we'll call it tau, the torque. Okay. That is the name given to it. So the force required to cause rotation. It's not simply pushing an object when it is moving. No. Does the force you apply causes rotation? Then that is angular force. F rotation can be given as rate of change of angular momentum from Newton's law. So I'll call it tau, I told you. So dl by dt, okay, which we call it torque here. Angular force is torque, tau. Now L is equal to m into r cross v, right? So tau is equal to d by dt of m into r cross v. Again, look at the terms here. Look at the terms very clearly. When an object is rotating, its mass is a constant, its radius is a constant, only its velocity is going to change. Mass is a constant, radius is a constant, velocity is going to change. So d by dt is only going to act upon velocity and mass and radius can be taken out. Okay, so mr into dv by dt, dv by dt is what? Rate of change of velocity, which is nothing but acceleration. So I've got tau is equal to m into r into a, or m into a is f. F is equal to ma formula, you all know. So m into a will become f, therefore tau is equal to r into f. Now here it's a little bit reverse direction. The angular force is equal to radius times linear force. Earlier it was linear velocity is equal to r times angular velocity or displacement or acceleration. But here angular force is equal to radius times linear force. So this is the formula for tau. Again, when I speak about directions, it's r cross f. I've got r, I've got acceleration. So f is along the direction of acceleration. Okay. So you can put it like this. The velocity changes, there's an acceleration. Okay. Angular momentum, angular momentum changes. So you've got a direction of angular acceleration, and that is nothing but the direction of torque. Okay, so these are all along the same direction. Fine. Now, where is this torque used? You use torque when you use a spanner, basically, because the rotational force, the force required to cause rotation, depends not only on the force you apply, but also on the radius. That means if the radius is very large, the force can be small. Even then you'll get torque. If the force is large and the radius is also large, the torque is very, very, very high. So when you use a spanner, you try to hold the spanner as away from the bolt or the nut as it is, which means you're going to increase the radius. Here it's given as L. So if L becomes very large, the force also becomes, or the rotational force becomes very large. You can apply a very small force also and rotate the nut where required. So this is the pictorial representation, okay, of all the vectors. This is another picture of the same thing. You hold the spanner. You never hold the spanner near the nut or the bolt, right? You always hold the spanner so far away from the, basically the nut. So the radius r should be large. Then the force applied by you will simply multiply by r. and the direction is along the arrows that's shown here in the middle. Okay, fine. And this is what led to Archimedes saying that give me a lever long enough and a fulcrum strong enough, and I will move the world or I lift the earth. Why? Because if you have a very, very, very long lever, then you put the earth at one end of the lever, and then you put a fulcrum very close to the earth. Okay, and because the lever is very, 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 very long, you can apply a very small force, and because of a very large radius, it is going to lift the earth with ease. So this is what Archimedes said. Day-to-day examples, if you're not going to use a spanner in your life, no problem. Day-to-day examples of torque is your door. You see, the door handle is always located on the outer side such that the radius is maximum for that door. Okay, and then the force applied can be very small to open the door. This is also the reason why when you try to close a window, if you hold the window near the hinge, okay, if you hold the window near the hinge over here, then it's very difficult to close the window. Whereas if you hold it at the edge, it's easy to pull the window close. So this is because of torque. Gears work in the same principle. Okay, as the gears have larger radius, there is more torque, or when the wheels have larger radius, there is more torque, and this is how the entire engineering branches work. Okay, because of torque. Now, well, let's talk about circular motion, constant circular motion, not just velocity acceleration of one simple arc. When you talk about constant rotational motion, circular motion, we know that at the point A, an object has the velocity A, VA, and at point B, we've got the object has the same velocity but along VB, right? So as the object is undergoing through a constant radius circular path, VA and VB may change, may not change, does not matter, but their directions do change. So I'll plot VA and I'll plot VB, and I'll just mix them up together to form the law of triangle of vectors. And when I do that, here I've got two sides of a parallelogram, and the diagonal of the parallelogram will give me the direction of the resultant vector. And here, because the velocity is changing directions, even then that is considered as change in velocity. And therefore, we have an acceleration which is pointed towards the downward direction, that is at the center. And this acceleration, because it's change in velocity, okay, because it's change in velocity, we put delta V, okay, and then you do this math, you will get this acceleration is equal to AC, which is given by V squared over R. It's given by V squared over R. And this is known as centripetal acceleration. Centripetal acceleration. Okay, we'll use this further. I'll talk about it later. So whenever there's a force, always there's a, whenever there's an acceleration, there's always a motion in the opposite direction. So let's talk about force acting on an object. We know the force acting on an object is equal to ma. So angular acceleration, no. Rotational acceleration, that is the centripetal acceleration, is equal to v square over r. Please do not substitute this as alpha. So centripetal acceleration is equal to v square over r. We substitute that. So we get x acceleration is equal to force by mass, or centripetal acceleration is equal to centripetal force by mass. Or let me just substitute F by m is equal to A, which is v squared over r, or F is equal to mv squared over r. So here, as an object is moving along a circular path, there is a centripetal force acting on the object, which is given by mv squared over r. So if an object is moving faster, velocity increases, numerator becomes big, force becomes higher. If an object takes a larger orbit, radius increases, denominator increases, the centripetal force is very small. And because whenever there's a direction of force, the reaction you have because of Newton's third law is going to be opposite direction. When the bus stops suddenly, the force is always in the backward direction. That's why you always move forward in the bus when the bus stops. When the bus starts, the acceleration is forward, so you'll move in the backward direction. Or the force is forward, so you move in the backward direction. Similarly, from Newton's law, we can say because the centripetal acceleration or the centripetal force is inwards towards the center, there is a pseudo force that you will experience which acts as outward direction. We call this centrifugal force. Okay, so this is the rotational mechanics that we'll be using. So centrifugal force is also used in roller coaster rides. You've got the loop to loop roller coaster. You can see here at one point, almost all people are upside down. Yet gravity does not pull them down. They may be wearing harness, but that is only to protect in case it fails. But by physics, those guys will not fall down when they are upside down in this particular loop because they are moving with very high velocity. And because the velocity is high, the numerator is high, and the centrifugal force in the outward direction, upward direction is high. So that force is greater than gravity, therefore they will not fall. When you look at MotoGP again, we've got the wires, the wheels spinning, and we've got so many forces, right? We've got the angular momentum or the rotational force, that is torque. We've got the centrifugal force acting outside the curve he's taking. There is the gravitational force pulling him down, which is supposed to make him fall, and the rotational force which he's applying the pressure on. Okay, he's trying to turn the bike. So all these forces are acting on him. Okay, and one more thing that I want to talk about is orbits, because most of the fascination that comes from rotational motion is because of planets. We all love looking at the night sky. We see Mercury, Venus, Earth, and we don't see Earth. We see Jupiter, Saturn, and Mars in the night sky, and we know they all go in circular paths. So even they should be following the laws that I've just mentioned before. So when you talk about orbit, let's take the moon and the earth for example. The moon and the earth are attracted to each other by gravitational force. Yet the moon does not fall towards the earth because of something known as the centrifugal force. Okay, so before we jump into the rotational mechanics of orbits, let's understand gravitational force first. Okay, this is from Newton's law. If there are two objects of mass m1 and m2 separated by a distance r, it's shown in the image, then m1 will pull upon m2 using a force F1, and m2 will pull upon m1 using a force F2. And Newton says these two forces are equal. And the force is given as F1 is equal to F2 is equal to G into m1 into m2 into r square. So F is equal to gmm by r square is a known formula to all of us. Now, when we talk about rotational motion in orbits along planets, then on a planet that is moving along the Earth, there is a tangential velocity given in one direction. There is a centrifugal force outwards from the orbit. And then we've got a centripetal acceleration or also gravitational force pulling towards the object. And because the moon is not coming towards the earth, it is always at the same distance from the earth, I can assume that the gravitational force and the centrifugal force are balanced or equal. So when I equate them, I've got the gravitational force gmm by r squared, which is equal to the centrifugal force, which will give me mv squared over r. And when I simplify this, I know here in the denominator, I've got an r and I've got an r squared. So r squared and r will cancel. In the numerator, both sides I've got an m, so they will also cancel. So when I've got the cancellation of m and cancellation of r, I have v squared on one side is equal to gm by r on the other side. And I don't like square numbers, so let me find the square root of things. So v is equal to root of gm by r, and that is the velocity required for the object to remain in orbit, such that when the object goes with this velocity, the centrifugal force, the v squared over here in the centrifugal force, becomes equal to gravity. An object can go faster and remain in orbit or leave in orbit. But an object, when it goes slower, the centrifugal force is not strong enough, so the object will fall towards the earth because of gravity being more than the centrifugal force. Okay. And any object that falls down with the acceleration, and we'll call this acceleration g. So that object is pulled down by earth with that force. So I'll write F is equal to gmm by r squared is equal to mg. Okay, g is the downward acceleration. Mg comes from Newton's second law. So F is equal to mg is equal to gmm by r squared. Simplify again. There is m in the numerator. I get g is equal to, small g is equal to gm by r squared. Or I can write gm by r is equal to gr. Okay, I'm just doing it for simplification purposes, because when I talk about orbital velocity, I have gm by r. So gm by r is equal to gr, which means orbital velocity is equal to root of gr. So for any planet, if you know the acceleration due to gravity, g, then you can find its orbital radius at some distance it's going to orbit, or you want to put it at that particular distance of orbit, you just put r into g, you multiply them and find the square root, and that is the velocity required minimum by the object to go in an orbit. Now, if you want to escape the gravitational pull, of course, your centrifugal force has to be greater than the gravitational pull. In such case, you need to have an energy, and this energy should be equal to the gravitational potential, or even greater, no problem. But minimum should be equal to the gravitational potential. So gravitational potential energy is given by gmm by r, and the energy of any particle that is moving away from Earth will be half mv squared. In which case, I just equate them and cross multiply the 2 and the m, okay? And I've got the m in the numerator in the kinetic energy formula here. M is in the numerator, so it goes to the denominator. I've got 2 here in the denominator, it goes to the numerator. So I've got v squared is equal to 2gmm by mr. Again, m and m will cancel out, and we've got v is equal to root of 2gm by r. This is known as the escape velocity. If you substitute the value of g, which is universal constant, 6.67 into 10 power minus 11, and if you substitute the mass of the Earth and the radius of the Earth, you will get the escape velocity to be 11.2 kilometers per second, which means to escape from Earth's velocity or Earth's gravitational pull, you need to have velocity which should be a minimum of 11.2 kilometers per second. So if you move up, exactly up with the velocity of 11.2 kilometers per second, then you will escape the gravitational pull and go away into space. Please understand, 11.2 kilometers per second is a very, very, very large number. It's very difficult. Okay, but we can still attain it using circular orbits. Okay, if you can see here, the cannon is shooting a cannon. Cannon is shooting a cannonball, and if it shoots something, it's going to fall down. You can see the first arrow over here. So the cannonball comes and falls into this arrow over here. But if the cannon shoots it faster, then it comes along this path and falls over here. And if the object is shot very, very, very fast with that escape velocity, then the cannonball will never fall into the Earth's surface. It will simply go and hit the cannon again from the backside. So if you want to escape the Earth's gravitational pull, you need to have a minimum velocity of escape velocity. At orbital velocity, it's going to orbit the Earth. More than that, escape velocity, it's going to escape the velocity of the Earth's gravitational pull. Okay. So with this, I think I will conclude this session on rotational mechanics. I've covered the basics of rotational mechanics: rotational acceleration, rotational velocity, rotational displacement, rotational force, rotational angular momentum, and so many other things. We've also discovered a few equations about gravitation. Okay, that comes from rotational motion. So that is also important. And with this, I would like you to solve two questions. Okay, I've given three questions. The first one is an easy question. The remaining two questions you need to solve. Okay, so you can take a screenshot if you're on the phone, or if you're on the PC, just copy this image. Okay, please read the questions. Let me just repeat the questions quickly for you. The first one says, what is the unit of torque and angular momentum? So you understand the formula. Torque is force into radius. Angular momentum is, what is that? MVR, mass into velocity into radius. So you put the unit for each of these terms, you will get the unit for torque. Okay? There is no named unit for these things, so it's just SI units. The second question, you look at that carefully. You've got the moment of inertia of a body about a given axis. So I is given, and that is said to be 1.2 kg meter squared. You've got moment of inertia to be 1.2 kg meter squared. And initially the body is at rest, no problem. Initial velocity is 0, angular velocity is 0. In order to produce a rotational kinetic energy of 1500 joules, okay, so it's going to produce a rotational kinetic energy. The energy has to be 1500 joules. An angular acceleration of 25 radians per second square must be applied. So angular acceleration alpha is given. Okay, that must be applied, which is 25, and they've given you the energy equation. E is equal to something, so it is 1500 joule. So you need to find out what must be the what do you say, duration of rotation for that energy of 1500 joules to be produced. Okay, so you have to find T. I've given you the energy formula. Okay, it's going to be rotated. So energy is 1500 joules. Angular acceleration alpha is 25 radians per second square, direct substitution. You're supposed to find T. Okay, and moment of inertia is also given. So I is also given. So look for a formula, or you take a formula and see if you can add another variable to it. I'm giving you a clue, okay? And see if you can find out an equation where I is already given, uh, what is that? Acceleration, alpha is already given, and energy is already given. You have to find the t. Another clue I can give you is usually the moment of inertia or the energy is on the left hand side, and the acceleration and time should be on the right hand side. So such is an equation you'll be using. And the third question that I want you to solve is very simple one. You consider another planet other than the Earth, okay? And this planet has mass three times that of the Earth. So you don't need to know Earth's mass. You just know that the mass of this planet is three times Earth's mass, okay? What would be the escape velocity of such a planet if Earth's escape velocity is 11.2 kilometers per second? That's a general value, all of you knows. Okay, so 11.2 kilometers per second is the escape velocity of the Earth. Find the escape velocity of the planet. So with this, I hope you can solve these questions. It's very easy, not very difficult. And if all of the things are right, I would like to conclude my session here. Thank you. Thank you, everyone.
Thank you very much, Dr. Atulji. Now I request attendees, if any questions, you can raise your virtual hand so that we can unmute you. You can speak to them directly and ask your question. Otherwise, if you have any question, quickly you can type in the chat box. Meanwhile, we have given the questions. You can write down or take a screenshot in your mobile or laptop or desktop, whatever, however you are attending this session, and write it down in the paper A4 sheet with the details of your college and name, and sign it and scan it and mail it to the email ID mentioned in the chat box. Okay, the best answer will be chosen by the speaker once again. Dr. Atul Bhaji will be going to choose the best answers, and they will be awarded cash prize from Academy. So I think there are no questions from the audience. Please do not hesitate if you have any questions. You can ask questions. Out of 3 questions here, they have asked you. Okay. If you have any queries, you can mention, or you can communicate with us through mail or WhatsApp group or Telegram group, or you can call us later or mail us. Then also we can communicate.
My email ID is also
Yeah,
there at the bottom of the
yeah.
screen, so
You
that
can
also
directly
helps.
communicate to Dr. Atul Bhaji also. He will be answering your queries if you have any in future also. Okay. So finally, we would like to conclude this session, today's session. Thank you very much, Dr. Atul Bhaji, for accepting our invitation and delivering today's wonderful session on rotational mechanics with real-time examples in our daily lives, so that we can see doors and doorknobs, window hinges, and everything, where we can see all the rotational mechanics. Even the space science also you have included, like planetary motion and all those things. I request students, if you read the textbook and go through formulas and just calculations, you will get bored to learn these new things. Try to associate the new things with your real-time objects wherever you see, and whatever you try to implement it. Then it will be interesting for you to learn new things. Like today, Dr. Atul Bhaji has shown you many things with the examples, the motion of the rotational mechanics and gears, how they work, even the door locks and the knobs, hinges. So with real-time examples, you will be able to understand better, and it will be very easy to remember you in future also. So the things cannot be forgotten very easily. With this, I would like to thank you once again, Dr. Atul Bhaji, formally
Thank you, sir.
on behalf of KSTA and on behalf of all the participants, and on behalf of all my colleagues. Thank you very much. Also,
Thanks.
I would like to thank all my colleagues who have helped us to make this event very successful. Few of them are technical team and a few of them non-technical team. But I would like to thank all of them. And last but not least, I would like to thank the participants, attendees, teachers, students who are attending in this WebEx Cisco platform, and also watching this session in YouTube live. Thank you. So I would like to thank you once again, on and all. Thank you, sir. Atul Bhaji
Thank you, sir.
will communicate with you in future
Sure.
also to deliver few
Sure,
more
sir.
sessions so
Sure,
that
sir.
it will be helpful for the students. Okay.
Okay. Thank you, sir.
Thank you. Thank you once again. Bye.
Okay, thank you, sir, Umesh sir.